This is Algebra 2 at Trig. This is the review for the final unit project. We're looking at three different equations. These three equations are actually equivalent to each other. They produce the exact same graph. This is standard form. So A is standard form. We know that because it's x squared, has an A value, a B value, and a C value. Over here, this is intercept form. We know that because we have two sets of parentheses, or sometimes it's not written with two sets. It would be x parenthesis x minus 5. There's only one set. But you're going to have two separate values. Here we have two binomials. It's possible to have a monomial and a binomial, but that's still intercept form. Here we have vertex form. Here we look at it, we have that one set of parentheses, but we have the square that's on the outside. That's what makes it different than a lot of the other formats. And we have our h value, our k value, so that's our vertex form. We're going to come over here and graph it. Well, when we look up here at our different formats, we have a lot of the information we need. We have the 2 for our h value, and then we got to go up 18. Now 18 falls off of this grid, so let's go up by units of 2. 2, 4, 6, 8, 10, 12, 14, 16, 18. There's the 18. So I know what the vertex form is. I see that my A value is -2. That means it's going to be opening down. We could find the points just by doing that. Over 1, down 2, over 2, down 8. But let's see what other items we know for sure. Intercept form. Intercept form tells us that we're going to cross at -1 and at +5. So those are two more points on our graph. And standard form tells us about our y-intercept. 2, 4, 6, 8, 10. Notice that that is 2 units away from the axis of symmetry, so I have 2 more units away from the axis of symmetry. So we can go right through here. Let's look for some other points. Parent function would be over 1, down 1, because the square root of 1 is 1. But this is times 2, so it's over 1 times 2. Remember, these units go by 2s. Usually down by 4, but now we're going to be 8. 2, 4, 6, 8. 3 should be 9, but we're going to be 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, and so forth. So there's our equation. I always like you to write it, so pick your favorite form. Well, we did the most damage using vertex form. It got us our vertex, so we didn't have to do all that line of symmetry stuff. So, using that, how high was the ball when it was launched? Well, when the ball was launched, we're using this area in here as our real world situation. Okay, I didn't read you the problem. The problem was all about you and your friend launch a ball from the top of the roof of a building. The height, which is your y value, is in yards. The x values are the seconds. And that's how long it's been launched. So in 1 second, it's up so much. After 2 seconds, 3 seconds, 4 seconds. Well, actually, nope. Those were by units of 1. So 1 second, 2, 4, 6 units higher than where we started, and so forth. So how high was the ball when it was launched? It was your y-intercept. And our y-intercept is 10 yards. And how long was the ball in the air? Well, the ball was in the air 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. 5 seconds until the graph reached the x-axis. From the 0 is when it started to go up in the air, and we were in the air all the way till the 5. What was the maximum height of the ball? "18 yards was the maximum height. This was the y value of the vertex. How long did it take to reach the maximum height? Well, we look here, we see the maximum height is up here, and it took 1 second. It takes 2 seconds to reach that maximum height. So two seconds. Line of symmetry. Line of symmetry is x equals 2. From the 0, we come out here to 2, so it took 2 seconds for the amount of time it was up in the air. How high above the launcher did the ball travel? Well, the launch, the height, the building must have been here. So it went up 2 feet, 4 feet, 6 feet, 8 feet. Or 8 yards. It's not really feet, is it? The units are yards for the y values. We could get that by saying 18, which is the max, minus 10, which is the shot location. That gives us the 8. How high was the ball after 4 seconds? Well, remember our x's were going by ones, so 1 second, 2 seconds, 3 seconds, 4 seconds. So it also looks to be 10. 10 yards. We know that because it's the reflection point of the y-intercept. Or you could plug in 4 into your equation. That could also work. How long did it take the ball to fall back down to a height of 16? Well, we're at a height of 10. 1 second, that was 12, 14, 16. In 1 second, it reached up to 16. Then it reached up to 18 after 2 seconds. Back down to 16 after 3 seconds. So one way that we could calculate that one, we could say 16 equals, now pick your form. What form do you like the best? I think that vertex form works pretty well because we don't have to factor, we don't have to use quadratic formula. We can go right through and just use square roots to solve such a problem. Take the square root of both sides, and we get plus or minus 1 equals x minus 2. So we get 1 equals x minus 2. We also get negative 1 equals x minus 2. So we'll add 2. We get 3 seconds. We also come over here and get the 1 second, but we wanted it back down, so that's why it was 3 seconds. It was hitting it on the second time it hit the height of 16. Fall back down, so that's why I'm picking 3 seconds. On the reverse side, we're looking for the work to transform the B equation into standard form. So what that means, we have to FOIL this. So we do the front, the outer, the inner, and last. Don't forget your -2 in front. So x squared plus 2x minus 35. Distribute that through. So there would be our standard form of equation B. Show the correct work to transform C into standard form. Well, notice how we have x squared. We cannot distribute that 5 through yet. We have to write the 3's twice. You got to square it, so you got to write it twice. So then we have to FOIL it. So to FOIL that, we multiply the first, the outer, and the inner to get to -6, and the 3 times 3 to give us 9. Now we have to distribute the -5 through. Now there's no need for parentheses because nothing's happening to that group of values. So our final answer has a C value of -49. We're going to transform the A equation into intercept form. Intercept form is essentially just factored form. So we need to factor this. So the first thing I'm going to do is factor out my GCF. I see that there's a multiple of 4 in each one of these. I'm not ready for the binomials yet, but this is x squared plus 6x minus 16. It looks like a +8 and a -2. What multiplies to be -16 and adds to be 6? 4 and 4 makes 16, but it doesn't add to be 6. 8 and 2 makes 16. I know we have to have a +8 because I need more positives left over. Show the work to transform it from equation A to vertex form. So this is called completing the square. So we're going to say 4x squared plus 24x minus 64 equals 0. I will bring my 64 to the other side. This is the important part. You need to write your factor. You can't have an A value of 1. You've got to factor out the GCF of the left side of your equation. Then you take the 6 and divide it by 2 and square it. Get 3 and square it to get 9. Now by putting a 9 inside those parentheses, it's really a 4 times 9. So I'm going to add a 36 to the opposite side. So when we complete the square, we're making a perfect square trinomial. That was the whole point. So our equation is going to be y equals 4x plus 3 squared. You have to include the square. Have to include that square. Subtract the 100 across to get -100. List the different methods you could solve a quadratic equation and describe it, or when it would be the most appropriate. Well, we could use, let's start with quadratic formula. For any of you that forget, that is going to be x equals -b plus or minus the square root of b squared minus 4ac all over 2a. That's your quadratic formula. When do we use that? When we can't factor. Use quadratic formula when we can't factor or don't want to factor or complete the square. We don't want to factor, or we don't even want to complete the square. We use the quadratic formula when we can't factor or complete the square. It's always a way. It works all the time. It just takes a little bit more calculations. Another way is factoring. Factoring is a great way if we can break it into two binomials. When is the most appropriate time to use factoring? When we can find the multiples that have a product of A times C and a sum of B. So when you can make the table and you can find your values when it breaks into two binomials, that's when we can use factoring. Not every quadratic is factorable. Another one we use is completing the square. We can complete the square when the A value divides into the B value. And we like the B value to be even, because we like to take half of the B value. You can also do graphing. And we can use graphing when the solution is going to be integers. So I've got 4, but definitely these top 3. That's the way that we would solve a quadratic. But graphing works. You're looking for the x-intercept, so maybe that's even better than solutions. When x-intercepts are integers, those are the solutions or solving. When the x-intercepts are integers, positive or negative numbers. We're going to solve this system. Well, if we're going to use substitution, we'll take x minus 3. Our y value is 1. And we have x minus 3 plus negative 4. We're squaring that. X minus 3 16. Subtract the 16 to the other side. Equals 0. Take the square root of both sides. So we get 3. Then we can plug 3 back in to find our y value. So we get 0 plus y minus 5 squared. And we get y minus 5 equals plus or minus 4 after we take the square root of both sides. So y equals negative 5. So we would have a spot at 9, and we would have a spot at 1. And of course, we didn't have to do that because we already knew what y was. Y was 1. So really, that's not necessary. There was only one solution where y equaled 1. 3, 1. Were you certain it would have that many solutions when you saw the problem? A line could intersect a circle at 2 points or even none. So of course 1, 2 points, or even none. So when you start the problem, you probably expect it to have 2. But when we got going, we saw that where was it y equals 1 was just when x was 3. There's only one location where that happened at. So we don't really need this part. A little crazy. What functions from the graphing calculator would be useful in solving real-world problems involving quadratics? With the graphing calculator, by going to second calc, we could find the zeros of a function, we could find the min or max, we could find the intersection of a line and a parabola. So we'll call that the system. Involving quadratics. We could also use the regression, write an equation using regression. Right, an equation using regression. Those are when given points. We could also, if we were given an equation, let's make this a little bit nicer. And we graphed it. Okay, a little bit further down than expected. So a minimum value of negative 30. There we go. Okay, we could use calculate, which is second trace, to find, yeah, we already said that, to find the minimum value. That's left bound, right bound. First you need to be to the left of what you think the answer is, and then to the right of what you think the answer is. And then your guess, that's just being nice to get close. If there's more than one answer, it's very important. So you can figure out what those locations. But we did that with min and max. That's your vertex. Okay, that'll do it for me. Anybody think of some others? Okay, we're going to use these graphs. Describe how the above graphs have transformed from the parent function. Well, the parent function would have gone right through here. So now it looks, that's 2, that's up 2, so it's translate 1, 2, 3 to the right. And 0 units up. And then from there, we rise up 2 and we go over 2 and we land right on it. So it doesn't look to be any stretching involved here. This one, here we're going from the 0 to the left, so we're going 2 units left, and we have a stretch that typically goes up 1 is now going up 3. So it looks like it's being stretched by 3 units. Vertical stretch of 3 units. And translated left 2 units. There's the parent function. So we're having a reflection. Over the x-axis. That means we multiply all the values by -1. And what typically goes over 1, 2 is only going up 1. 1, 2 usually goes up 2. We're only going 1. So it looks like it's being shrunk. By a factor of 1/2 and translated 1 unit left, 2 units down. Write the equation of each graph. Well, that's going to be in the format of a x minus h plus k. So my a value is 1 because the slope is 1. And it's being translated to the right, so it's -3. This next one seems to have a vertical stretch. Oh, I said 3 units. I'm sorry. A vertical stretch scale factor of 3. Vertical stretch by a scale factor of 3. So we have a 3 in front and an absolute value bar, x plus 2 minus 0. And then this last one, we said that it had a reflection, so it's negative, a vertical shrink, or it has shrunk by a half, and it's translated 1 unit to the left and 2 units down. The domain, all real numbers, every absolute value is all real numbers. The range for the first graph are the y values greater than or equal to 0. There's our intercept form, or interval notation. This, our domain, would be all real numbers, and our range is, again, which would be y is greater than or equal to 0. Our domains are real numbers, and our range, the y value was less than or equal to negative 2, which would give us a negative 2, but that's actually the highest number. So the smallest number, when you write interval notation, you always write the smallest number first. For what values of n will the equation have no solution? So we're looking for no solution here. That means our absolute value we want the absolute value isolated all by itself, and now we want to know when n minus 4 is less than 0. When it's less than 0, when it's a negative number, you're going to get no solutions. An absolute value cannot equal a negative number. So you add your 4 to the other side. So when n is less than 4, that's what's going to make the absolute value portion equaling a negative number. So you can try that. A number less than 4 would be like 3. If you put a 3 in here, you subtract the 4 from the 3, you get negative 1. So the absolute value equals a negative 1. An absolute value can never equal a negative number. To get a solution of 1, we're going to have the n minus 4, not a solution of 1, but only one solution. When does it equal 0? By equaling 0, you're not going to plus or minus anything. There is no value. There's not two different values to equal to 0. There's only one way to get 0 for this problem, and it's when x is 5. Two solutions is when the n minus 4 is going to be a positive value. So to do that, we're going to have, I can show example. Add 4 when n is greater than 4. So x minus 5 plus 4 equals 8. So minus the 4 across. And then x minus 5 equals 4, and x minus 5 equals negative 4. By adding the 5 across, we get one answer, which is 9, and we get another answer, which is 1. So we get two different answers when your n value is greater than 4. Two solutions. We get only one solution when your n value equals 4. n minus 5 plus 4 equals 4. By subtracting the 4 across, we get 0. Well, you can do the plus or minus concept here. There's two different ways to get 4 from an absolute value. It can be a negative 4 inside, or it could be a positive 4 inside. Either way, the absolute value bars make it look to be positive. Well, here there's only one way for us to get 0, and that's when your x value is 5. And on this side, be this very similar, you would plug in a number less than 4, and that would give you a negative answer that's your absolute value equal. On the final side, we're going to look at these tables, and we're going to consider if the table models an absolute value function or a quadratic function, or apparently neither. And we're going to explain how we know it. So, to determine, one thing we could do, we could look at a sketch where 0, 48, and 121, and 2, 0. At 3, we're at negative 15. At 4, we're at negative 24. So it's not going down quite as much anymore. At 5, we're at negative 27. At 6, we're back at negative 24. And then it starts to head back up. So it didn't seem to be following the same slope. Well, that's one way we could do it. Not very mathematical. What I would suggest doing at trying to determine what type of equation we have is 48 minus 21 gives us 27, gives us 21. 0 minus 15 or negative 15 is positive 15. Minus gives us 9. Minus gives us 3. Minus gives us a negative 3. And minus gives us negative 9. So we look at those at the first degree that we did this common difference. We got a different number. But we do it again, and we see that the difference is 6. 27 minus 21. 21 minus gives us 6. 15 minus 9 is 6. 9 minus 3 is 6. 3 minus a negative 3 is still 6. Still 6. So now you look at that common difference. It's the second degree, so we know it's a quadratic. We know that the a value, it's not 6, it is 6 divided by 2. So that is our a value. So y equals 3. What else do we have here? We have the 24 is repeated, the 15 is repeated, so here is our vertex, our h and the k. So x minus 5 quantity squared plus a negative 27. So we know it's quadratic because the numbers are not changing at a constant rate. That was our first little test. Our second test was at the second common difference. The second difference gave us a common value. We know it's quadratic because the common difference appeared at the second degree. Or it's called the second common difference. This next one, we look for a vertex, and we have the same numbers being repeated, so we get this vertex, this h and k value. But I still need to determine if this is linear, are the numbers changing at a constant rate, or is it quadratic, where it's going to be the second degree to finally get that common rate. So we look here at negative 7 minus a negative 5 gives you negative 2, negative 2, It looks like I'm getting 1 minus a negative 1 is negative 2. I'm getting my common difference to be in the first degree, or to be the first common difference I do. So now I know that this is an absolute value. I know it's not a linear equation because the values go down towards, let's see, we have a y value, so they're actually increasing up to the 1, and then they're decreasing again. So it's an a value that is upside, or it's an absolute value that's upside down. So we do the negative 2 divided by 2, which is negative 1. Well, wait a second. This is just showing our slope. Okay, so we have slope of the negative 2. We don't take half of it. Sorry. Y equals, for the absolute values, negative 2, the absolute value of x, minus 6, positive 1. And you can test this theory by taking in any number you want, taking the 3. So 3 minus 6 is negative 3. Absolute value, that is positive 3. Times negative 2 is negative 6. Plus 1 is negative 5. So you can test any numbers you want. You could do the same thing up here with this guy. You could plug in 2 to get 2 minus 5, which is negative 3. Square it, which is 9. Times 3 is 27. Minus 27 gives us 0. You can test it with any point that's part of it. So we know it, meaning the table, it's an absolute value because the common difference appeared at the first degree. It was the first common difference that happened at. So now we look at the numbers where they repeat. We go 12 and then down and down and down and down and down and down and down. It looks very much like this is going to be linear. We don't bounce back up. If we looked at a quick picture of this one, we're at 2 and negative 7, 3 and negative 5, 4 and negative 3, 5 and negative 1, 6 and 1, 7 and negative 1, 8 and negative 3, and it came back down again. Well, in this case, we're at negative 4, 12, negative 3, 9, 2, 6, 3, 1, 0, 0, and we're still heading in that same exact direction. The common difference is 3. 6 minus 3 is 3. Minus a negative gives you 3. Okay, we know that this is going to be linear. We have our first degree. Now, you notice that it is consistent. It is common. Looking at this, we always start with a negative 3 to the 4, and it's increasing by 3 each time in terms of a y value. But when we think about the slope, we're looking at a negative y when the x was positive. Negative y when the x was positive. So that's actually going to give us an m value of negative 3. and our y-intercept is at 0, so plus 0, so that's our equation. The data shows a common ratio of y is changing by -3 and the x is changing by 1. For a rise over run, y over x, the y value went down 3, -3, when our x went up 1, which is positive 1. 1 bigger each time, went down 3 more, down 3 more. These numbers are correct in terms of the 12 minus a 9 and a 9 minus a 6. We get that common ratio, but it wasn't really showing us the slopes. Okay, last one. For a table that models a quadratic function, write an equation of the function in the two forms you didn't already use in the space below. Show your work. Models a quadratic. That's the one up here. And for the two that I hadn't done, I've already done vertex form. Vertex form was y equals 3, x minus 5 squared minus 27. So now I need to come up with intercept form and standard form. So we look back at the one we call quadratic. We don't know what the x-intercepts are. When y is 0, we're up at 2. So that's going to be the next one. So 9 gave us to the 15. And 9 more is going to take us to the 6. Well, actually, it's not going to be 6. It's going to be 0. Our pattern here. So it's going to be up here at 8. Let's try that. That would be one method to do it. We could also, to help us determine standard form, the most obvious way is going to be 3 times x minus 5 minus 27. We're just going to multiply this out. We'll write the binomial twice. We have x squared, and we multiply through to get 3x squared minus 30x plus 75. So our equation is 3x squared minus 30x. That would be 48. Positive 48. We could test the two if we had a calculator available to us. So we put in the 3x minus 5 squared minus 27, and we put in the 3x squared minus 30x plus 48, and when we look at the table, I'm expecting them to be exactly the same. Great way to test it. You can plug in a point and see what happens. It's another way. So the one that we don't have is intercept form, and I'm going to take my 3x squared minus 30x plus 48, and I'm going to factor out my GCF, and that's going to leave me with a -8 and a -2. And we can test that theory also. We can come up to 3 times x minus 8, x minus 2, And when we check the table, they should be exactly the same, and not quite. Let's see, what did I do wrong, anything? Oh, it has a squared at the end. What happened with that? Three x minus 8, x minus 2. There's our numbers. Now they work out perfectly. Had more in that equation. So, good luck.